All right, we're all teed up now. We know what the receiver operating characteristic curve is, and now we're going to learn how to use integral calculus to find the area under it. You may recall from one of the very first slides in this calculus live lessons, we talked about integral calculus being the study of areas under curves. So it facilitates something like the opposite of differential calculus. So in the same way that differential calculus allowed us to take a chart of distance over time and convert that into a chart of speed over time like we see here, integral calculus allows us to make the opposite kind of inference. So it allows us to add up the area under a given curve. And so in this example of a vehicle traveling and where we have speed over time, that area under the curve corresponds to the total distance traveled. So when we're on the freeway here, there's a chunk of distance that we're traveling, and it corresponds exactly to the amount of area filled in under this curve. And same thing, there's a chunk of distance that we covered here on our way to the store. While we were at the store, we had no speed, so there's no area under the curve, and there's no distance traveled. In addition to finding areas under curves, integral calculus also allows us to find areas more generally. It also allows us to find volumes and central points. But for our purposes in these live lessons, we'll focus on area under the curve. It might be kind of self-explanatory, but the reason why we're focusing on finding areas under the curve in these live lessons is because it's finding area under the curve that is the most relevant application of integral calculus to machine learning. So, for example, the receiver operating characteristic that we now know how to calculate, if we want to find the area under that curve, we use integral calculus. We can also use integral calculus for other applications to machine learning, like the probability theory expectation of a random variable. This is a concept that is widely used in machine learning, including deep learning, and we will talk about that later in my Machine Learning Foundation series outside the scope of these current live lessons when I talk about my probability and information theory subject. Also, how does integral calculus work? Well, in the same way that differential calculus uses the calculus of the infinitesimals to find an infinitely small distance between 2 points and identifying the slope of the distance between those two infinitely close points, in integral calculus, we rely on infinitely small slices of area underneath a curve. So let's look at an example. So let's say we have this curve here, this relationship between x and y. If we have a large delta x, and then we calculate the volume of rectangles that fit under our curve, well, that's one way that we could try to identify the area under our curve. But using big delta x's like this, you can see we're missing a lot of area. So all this white space around here. If we make our delta x smaller, then our rectangles more accurately fit the full area under the curve. We still have some missing bits, but by approximately halving delta x from this situation here to this situation here, our filling of the area under the curve is more comprehensive. So following that logic to an infinitesimally narrow rectangle to an infinitesimally small delta x, then we could fill in the entire area under our curve. And so to represent an infinitely small delta x, we use dx to indicate this kind of slice width, this rectangle width that is approaching zero width. Speaking of integral notation, let's dive into it a little bit deeper. So here is that dx term here. So you'll see lowercase dx, that d will always be a lowercase d, but then x is whatever variable we're integrating along. So in our examples here, we're integrating along the x-axis. meaning that we're integrating along this axis here. And so we're using dx. So this denotes what variable we're integrating along. The second part of our integral notation is to indicate what function we're integrating. And then the third and final part is to have this funky looking, maybe kind of cool looking integral symbol. And specifically, this is the indefinite integral symbol. Later on, I'm going to show a variation on this of something else called a definite integral. Okay, so to understand why it's called an indefinite integral, let's start tackling some integration rules. So, in the same way that in differential calculus we had a power rule, and it was one of the first rules that we learned in differential calculus, the power rule is also typically one of the first rules that we learn for integral calculus. So this integral power rule states that if we're integrating this function x to the power of n, that, remember with differential calculus, we go from xn to xn minus 1, well, then maybe it shouldn't be that surprising that with integral calculus, which is kind of the opposite, we go from xn to xn plus 1. But there is an added twist with the integral power rule where we have a denominator that is also equal to n plus 1. And so this is analogous to in differential calculus where we grab the n and bring it out in front of the x. This is the same kind of thing happening with our power rule for integral calculus. Now note here that then of course we cannot calculate the integral with the power rule if n is equal to 1, because then in our denominator here we would have a 0, and you cannot divide by 0. Now finally we get to the point where I can explain why it's called an indefinite integral, and that's because there could be some constant that may have been lost by differentiation. So remember, when we calculate derivatives, if there's a constant in our function in a separate term, that constant is lost. It becomes a 0. So then if we were taking that function that we'd calculated with a derivative and we tried to reverse it back to an integral, we'd be missing that constant, and we wouldn't have even known that it was there. So what we do when we're calculating an indefinite integral like this, where there could be missing information, we add this plus c notation to indicate that maybe there was some information there that has been lost. Okay, and then to make this rule clear, let's look at some numbers. So let's say we have this function x to the power of 4, and we want to calculate its indefinite integral. Then, according to the power rule, x to the power of 4, we add 1, becomes x to the power of 5, and we take that same number and throw it in the denominator. So the indefinite integral of x to the power of 4 with respect to x is x to the power of 5 divided by 5 plus c. Don't forget that constant that might have been lost due to earlier differentiation. Nice, so that's the power rule. Let's go now to the constant product rule. So we talked about that with respect to differentiation. It was one of our most important differentiation rules. We've used it tons of times now in these live lessons. Let's find the integral analog of it. Okay, for the constant product rule, this is just as simple, actually, as it was as a constant product rule for differentiation. All it means is that if we are integrating some function with a constant in front of it, we can throw that constant in front of the integral, calculate the integral of our function, and then bring the constant back in later on. Note that we still need to be accounting for the possibility of a constant that was lost. All right, let's bring some numbers into the picture here. Let's say we're integrating this function 9x squared. Well, we can grab that constant 9, throw it in front of the integral operator, calculate the integral of x squared, which is x cubed divided by 3. And then after we've calculated that integral, we can bring the 9 back into the picture seamlessly. Don't forget that plus c. And we have some nice simplification we can do here. 9 divided by 3 is equal to 3. Nice. All right, and final integral rule I'm going to teach you, the last one that's in scope for us, is the equivalent of the sum rule from differentiation. We've got the sum rule for integral calculus as well. The sum rule for integration is just as simple as it is in differential calculus. We can take two functions that we're integrating, and we can integrate them separately, and then add the resulting separate integrals together. And as usual, don't forget that constant c for some constant that might have been lost. Looking at this with some numbers, let's say we're integrating x to the power of 4 plus 9x squared. Well, we can just integrate these separately. So the integral of x to the power of 4 is x to the power of 5 divided by 5. And the integral of 9x squared is 3x cubed, as we saw on the preceding slide. Put the plus c on there, and we're all good to go. Nice, so that's it for indefinite integrals. Well, that implies that there is something called definite integrals, and there is. Those are coming up next.